So in this class, we're going to look at representation of vectors, but now we will start by looking at things similar to what you guys did in first year, but then we'll start adding bits and bits of information or detail that you guys are going to find useful going forward. Now, I have to say the concepts you're going to learn in for the first few lessons are going to be very useful um, in this course in the sense that they are all based on the same thing. I think the first three topics are going to be very fundamental. These concepts will be useful in terms of solving questions that you guys will see in the third topic. It's like we're literally building on to the third topic. And once you reach the third topic, we'll start looking at that topic in different ways. So the topics that will follow after the third topic will just be different ways of representing, like basically just complicating the third topic that you guys will see. Anyway, we start with the vector. This course we'll be looking at forces and how the forces affect structures, and forces are vectors. So this is why we're trying to understand different ways of handling vectors. So you guys have seen a vector representation as an arrow in this form. And you know to say that if you are given an angle somewhere here, and you are given the magnitude of the vector, let's say A, you can easily resolve the vector to get its horizontal component and also to get its vertical component. These methods you have seen from your first year studies. Now, what you want to also show you guys is a trick or some detail that they might give you. Instead of giving you an angle, they might give you something else. And that information should also be useful in finding a way to actually get the components of a vector. Now, let's say you have some vector like this. Let's place an angle here to be, let's say, 20 degrees. And then you have a vector of magnitude, let's say 100 newtons. You know to say if you wanted to get the components of that vector, you can say its x component will be 100, and then this will be cos 20 in newtons, and then its y component will be 100 sine 20, also newtons. But what if you do not have an angle? Instead, you have something like this. Now, what they like doing in this case, so I can give you this to say this is 100 Newton, but instead, they'll give you some shape here, weird shape that looks like this. So instead, you have something like this, and then they'll relate. They'll tell you to say that, okay, this part here, so I want this to be more vertical. That's not going to be vertical. Let me do this. This looks better. Now I'll just make it smaller. Better. So I'm given something like this, and okay, so you have something like this. Then what they would do, so let me just make these to be bigger. Okay, so they'll give you the sides of this triangle that we have here. They will tell you to say that its vertical part, we can give this a 4, we can give this a 3, and then they'll give you that to be a 5. Now, what you have to see is that you can also use this triangle to actually also resolve that vector into its pieces. So in the original way, you are comfortable from first year to resolve a vector given an angle theta and the magnitude of the vector. But what if you're given a triangle here? Well, you have to see that you can actually use this triangle to figure out the angle that can be used here. And then once you figure out what that angle is, then you can go back to break down that vector into its components. So you have to see that. The logic here is quite simple. You see, The small triangle there has sides 5, 4, and 3, and an angle at its base here as theta. This theta can easily be determined. So you can easily determine this theta here. You can easily say that, okay, if I had cos that theta, you can easily say cos is adjacent, which is 3 in this for that small triangle, over hypotenuse, which is a 5. You can easily do that. And if you want, you can actually even calculate what that theta is going to be by just saying theta is equals to cos inverse of 3 over 5. So this is going to give you what theta is. Once you know what that theta is, you have to see that that theta can actually be related to the theta at the bottom here, the theta for the bigger triangle. Why and how is that even possible? Well, quite easy. Quite simple. You see, the angle here, you have to see that this angle here is in fact the same as this angle here, provided that this line is parallel to this line here, which will be the case in most cases where you encounter this problem. So because of that, if this angle is the same as this angle here, you can easily use the red triangle here to figure out what theta is. And once you know what theta is here, then you've gone back to that basic case where you have an angle and you have a magnitude of a vector, and then you're trying to find the components of that vector. So it has transformed back to the basic form that you are actually aware of. Are you okay with that first part? I repeat, which part? Okay. So we have the big triangle as this. And then we are given its smaller version. Its smaller version is there. Now, what I was trying to say here is that if we are somehow able to find the angle here as 30 degrees, then you have to know that even the angle at the bottom here has to be 30 degrees. So what they will do in this case is that they will give you enough information for you to find an angle from the small triangle. But once you can find an angle from the small triangle, then you have enough information to actually figure out an angle for the big triangle that you can actually use to resolve your vector. Have you got that? Yeah. So you can actually find the angle directly, like the way we've done, the way I was saying, do cos inverse and the likes. But what they like doing, what you will see in some books is that if the vector is given like this, and then they give you a small triangle like this, they give you 4 here, they give you 3 here, they give you 5 there, and then you have maybe a theta here. Instead of going directly to find theta, they'll do this. They'll say cos theta is equals to 3 adjacent over hypotenuse. Then they'll also say that sine theta, sine is opposite over hypotenuse. They'll say this is 4 over 5. Now, instead of evaluating to find theta, which you can do if you want, they'll actually just leave it at this, but they'll respect or observe the fact that even the angle at the bottom here is still theta. Meaning, if you now want to find the components of the vector, you will still say that, okay, this is your horizontal component and this is your vertical component. Let's say the vector is 100 newtons again, meaning to get its horizontal component, you will say it's the 100 newtons and then cos the angle here, theta. And then to get the vertical component, you say it's 100. And since the angle relates there by sine, that will be sine theta. But based on the small triangle, you did observe that cos theta is 3 over 4. And sine theta is 4, not 3 over 5. And sine theta is 4 over 5. So even without knowing exactly what theta is, you know to say that cos theta is 4 over 5. Meaning that this can now be written as 100. And then in place of cos theta, now you put, so cos theta is 3 over 5. So in place of cos theta, you have 3 over 5. And here you have 100. And in place of sine theta, you put 4 over 5. Have you seen that? Great. Now, this is everything you need on this method of handling vectors. Now, to help you guys just picture this, let's look at some questions that you'd encounter in first year physics, but now added with this twist that we've just looked at. Consider this example. And in this case, we're just going to work out this. We won't look at this one just yet. We'll look at this later. So let's look at this one here. So what is happening here? They're saying, in each of the following, determine the magnitude and direction of the resultant force. And then they're saying direction is measured anti-clockwise from the positive x. So this is a typical first year question. Of course, maybe a bit more realistic in the sense that they're using an object that is a real life object. But otherwise, it's still the same concept of resultant force given three force vectors. Now, the difference here from first year is that in this case, you actually have this force here, which is represented in terms of those that small angle there that we just from describing earlier. So we want to see exactly how we are going to use the concept we are describing to interpret that part. So how do you solve this from first year? Well, easy. So in first year, you just would say create a table so that you can account for all the vectors. There are three force vectors there. And since that is a two-dimensional space, so you only are interested in the x component and the y components. So we have first one, I'll label it A, B, C, and the resultant will come here. So how do you resolve the vectors? So I'll start with this one as my force vector A. The entire vector points in the horizontal axis and it points to the right. So that is a 300 newtons to the right in the positive x. I'll be a little bit quick with these because they are things that you guys have been doing since first year. I'll only relax to interpret that because it's the only new thing we're doing here. But if I leave you at any point, feel free to bring me back so that I spend a bit of time there. So the whole 300 is in the positive x. So I'll write that 300 here. And it doesn't have anything in the vertical axis. So that is going to be 0 in the y-axis. That sorts out the 300 newtons. And then I go to the 400 newtons. The 400 newtons is like that. And the angle between it and the horizontal is 30. So this can easily be resolved. That's a 400 cos 30 in the x-axis. That's a 400 cos 30. And then in the y-axis, that's a 400 sin 30. And then we go to C, which is the highlight of the show. So for C, look at how they're presenting it. We have this. And then the force vector itself, it's has magnitude of 250 newtons. But instead of giving us the direction, they've given us a small triangle. So what are they saying about that small triangle? They're saying it has a hypotenuse of 5, base of 4, and vertical part of 3. So this is what we have there. So what are we going to do? We can pick this angle here to be theta, meaning that even the side here is going to be, the angle there is going to be theta. So based on that, we can now try to determine what cos theta is. So we can say cos theta. Cos is adjacent over hypotenuse, so it will be adjacent 4 over hypotenuse 5. In the same way, we can say sine theta. Sine theta is opposite over hypotenuse. The opposite is 3, the hypotenuse is 5. So if you're not comfortable with this step, you can easily just come up with one, then do the math to find what theta is, and then bring it here and use the original technique from first year. Okay, so we have cos theta, we have sine theta. Now we can easily get the components of that 250. So we have the horizontal component points like this. It points to the left, so remember to give it a negative. So this is going to be the x component will have a negative, and it should be the 250 itself. But it will be cos the angle theta. But you know what cos theta is? It's 4 over 5. So this is minus 250, and then 4 over 5. So this becomes minus 5 into the 250, 5 into the 25, that's 5 times. So we have minus 5, 0 multiplying 4. Then 4 with 5, that's 20. So you guys can easily just verify what I'm doing here and have a calculator with me. In the same way, you can get y. Y points up. So it will be positive, and it will be 250 sine theta. So this will be 250. Sine theta is 3 over 5. So from here, we can do the math again. 5 into 25, that's 5. 5 by 3, that's 15, giving us a 150 here. So I have minus 200 and 150. Any questions here? Yes. Let's go on. Go ahead. Okay. So for the x component, I observed the fact that this vector points a little bit to the left. The vector is like this, right? So if it is like that, the x component, remember you always start from the tail. The x component will point from here, coming like this. So it's the fact that the arrowhead points to the left why I dropped a negative. Here, I chose this approach because the angle I am using here is this angle theta. In the method where you do not observe direction and assign the sign in advance, you must use the angle from the positive x anti-clockwise until when you reach the vector, like that. If you were to use this angle instead, you could have done it without presetting the direction to be negative. Do you get my point there? Yes. Yeah. But because I just want to use the acute angle wherever it is, I have to observe the direction. So I say I observe that this x component goes to the left, so the x component must have a negative. Then the magnitude is a 250, and then I can say cosine that angle theta. This is where the negative is coming from. Notice that even when I was getting the y component, First, I checked where it is pointing. It is pointing up, so it will be positive. So I know this will be positive. It will be 250, and it will be sine. Yeah. Have you got that? If you are not sure on how to use this, let's take theta. Let's take something like a vector that is more like this. And we know the angle here to be 30 degrees. You see, if the angle there is 30, then measured from here, it will be what? 150, right? So when getting the components, if I decide to use the 30 degrees, I must observe that this component points to the left. And because of that, I'll preset a negative here. Let's say this is, let's give it just 100. So this would be minus 100, and that is cos 30. When you solve this, what are you going to get as the answer? What's that? 6.6. Okay. Okay, so let's say this is newtons. Now, notice that if I was to use the 150, there would be no need for me to put a negative here. I'll just write 100, and this will be also 150. I am measuring the angle from the positive x anti-clockwise to the vector. Observe that it will give you what? Try to punch this again. What are you going to get? It gives you the same, and it actually brings the negative even though you didn't include it. So this is why I said, because I've chosen to use the angle exactly where it is here, I must observe my direction. So this is why for this one, because I chose theta to be here, which is this, I have to observe that this points to the left. Are we okay now? Yes. Great. So now we can proceed. So we are here. We have figured out the components. The remaining part, add these. What are you going to get? What's that?
Okay, I was saying you'll get the result on X component. So
Yeah. What did it be?
that's 426.4.
Okay. Now add this. Is this 350?
Uh, 350.
Okay. Okay. So yeah, just verify this. Make sure it's giving us that 400.
Yes, the math is okay.
Ah, great. Okay. So once we have obtained this, we can now calculate the resultant, the magnitude of the resultant. To get the magnitude of the resultant, Pythagoras, the x component squared plus the y component squared, then square root. What are you getting?
567.26.
Okay, so this becomes the magnitude of the resultant. Next, the direction. To get the direction, you have to use tan inverse. But what I like doing is to first picture the resultant. So we'll graph it so that we understand where the resultant is. 122 is not possible. It's possible actually. 122. And not possible. Look at this is too big. This is too big. We can't get 125. Try to redo it again. Because if I have 9 squared plus 4 squared, and then I square root, it can't be anything less than 9 or less than 4. Have you got that? A good example. Okay. A good example is which one? 4 squared plus 3 squared. The answer can be less than 4, it can be less than 3. So this is 16 plus 9, which is 25. And we see that we get a number greater than both of them. So that's why perhaps this is correct. Okay. So I want to just picture my resultant. For me to picture it, I will use the components. So the components of the resultant, all I want to see is, are they positive or negative? The x component is positive. So the x component goes like this, the positive x-axis. The y component is also positive, meaning it goes up, the positive y. So this allows me to visualize my resultant, to say it's a resultant that actually points in that direction. So when I'm finding the direction, I am actually finding an angle that starts from the positive x, anti-clockwise coming there. This is where that direction theta is. So this is actually fine. So I can easily say theta is equals to tan inverse of the y component, which is 350, over the x component, which is 446.41. So what are we getting here?
That's 88.097.
So let's just say 38.1. So this becomes our direction. The question wanted what? Determine the magnitude and direction of the resultant. So there we have it. The magnitude is 567.26 newtons. The direction is 38.1 degrees. Are we okay with that? Okay. Now, with that sorted out, the next example that we have is this one here. So it's kind of similar to the previous one, but now just observe that the difference is in the direction of the force vector F3. Mind where this arrowhead is pointing. That is going to change how you actually find the answer. But just like in the previous question, the question here is find the magnitude and direction of the resultant vector or the resultant force here. So this is what you want to find here. But I'll let you guys try this one out. So please try to work it out and let's see what you're going to find. Let's see if you understand how you actually deploy this. Quite similar, not really much will be different here. Any questions on this one? Okay, so looks like we're good.